So let's see if we can calculate a few things about that crash video that we just saw. So one of the things we'd like to find out is what was the velocity of the bus in the y direction after the crash. The bus driver claimed that he barely felt it, so that would indicate that the bus didn't move very much after the crash. And then also, what is the average stopping force on the motorcycle if it dents the bus a distance of 10 centimeters? All right, so let's first off draw a picture where we reproduce what the vehicles are doing, at least right before the crash, and set up our coordinate system. So let's say here's the bus, and let's say that the bus is traveling in the x direction. So this would be the positive x direction, and this would be the positive y direction. Then the motorcycle is traveling in the positive y direction before the crash, and the bus is traveling in the positive x direction before the crash. So let's analyze the motion before and after the crash, and let's focus particularly on the y direction. So if we look at the motorcycle, initially, we're told, was traveling 55 miles per hour before it hits the bus. So the initial velocity of the motorcycle in the y direction is 55 miles per hour. And of course, we want to convert that into meters per second. So 1 mile per hour is equivalent to 0.447 meters per second. So that means the initial velocity of the motorcycle in the y direction is about 24.6 meters per second. And the final velocity of the motorcycle in the y direction was 0. The motorcycle comes to an abrupt stop and transfers its momentum to the bus. So then if we look at the bus, its initial velocity in the y direction was 0. It was not traveling in the y direction at all prior to the crash. It was traveling in the x direction. And the final velocity in the y direction, that's what we're trying to find. We want to know how fast would the bus be traveling in the y direction post-crash if the motorcycle's momentum were transferred to it. The other thing we need to figure out are the masses of both vehicles if we want to conserve momentum. So we don't have precise values for this, but let's estimate that the mass of the motorcycle is about 100 kilograms. So that would be the motorcycle plus the rider. And let's say that the mass of the bus, on the other hand, would be much bigger. Let's say that's around 10,000 kilograms. Okay, so let us then conserve momentum in the y direction. So we want to conserve momentum, and we'll just focus on the y direction. We know that momentum is a vector, and like other vectors, we can analyze the motion in one direction at a time. So if we conserve momentum in just the y direction, so all of the quantities we are writing down now are y direction quantities, we would have that the mass of the motorcycle times the speed of the motorcycle, or the velocity of the motorcycle in the y direction initially, plus the mass of the bus times the velocity of the bus initially, is equal to the mass of the motorcycle times the velocity of the motorcycle final, plus the mass of the bus, velocity of the bus final. Now some of these we know are 0. Initially in the y direction, the bus is not moving in the y direction, so the momentum in the y direction for the bus initially is 0. And after the crash, the motorcycle stops and is not moving in the y direction, so that would be 0 as well. So then what we need to do is solve for the final velocity of the bus in the y direction, and we can see that this term is just equal to this term, so we can divide both sides by the mass of the bus. So the velocity of the bus final is going to be equal to the mass of the motorcycle, velocity of the motorcycle initial divided by the mass of the bus. So we then can plug in some values. Let's see, the mass of the motorcycle we're estimating to be about 100 kilograms, and the motorcycle was traveling 24.6 meters per second, and then we divide by the mass of the bus, 10,000 kilograms, and we get a final speed of the bus in the y direction of 0.246 meters per second. And if we want, we can convert that back to miles per hour. So 0.447 meters per second is equivalent to 1 mile per hour. And so that's equivalent to 0.55 miles per hour. So that is not very fast at all. It makes sense that the bus driver said that he barely felt anything happening. So the other question that we would like to answer then is, what is the average stopping force on the motorcycle if it dents the bus a distance of 10 centimeters? So to answer that part, I think what we can do is turn to the work energy theorem. Because we know that the work that's done by the bus in stopping the motorcycle is going to be equal to the force on the motorcycle times the displacement of the motorcycle. So how far did the motorcycle travel while the force of the bus was acting upon it? And then that's going to be equal to the change in the kinetic energy of the motorcycle. So change in kinetic energy is 1/2 mass, and this is the motorcycle mass, final velocity of the motorcycle squared minus 1/2 mass of the motorcycle velocity of the motorcycle initial squared. So we have this difference in kinetic energy is equal to the work. Now we know that the motorcycle comes to rest, so the final velocity of the motorcycle is 0, therefore the final kinetic energy is 0. And so we can solve for the force. So we just have to take delta x, the displacement, and divide both sides of the equation by delta x, and we get that the force is equal to minus 1/2 mass of the motorcycle, velocity of the motorcycle initial squared, divided by the change in the displacement of the motorcycle while it's in contact with the bus. So putting in numbers, the mass of the motorcycle is 100 kilograms, and the initial velocity of the motorcycle was 24.6 meters per second, and then that gets squared, and we divide by the 10 centimeters, or 0.10 meters. So if the motorcycle dented the bus a distance of 10 centimeters, then the force exerted on the motorcycle would be 3.03 times 10 to the 5th newtons, which is a sizable amount of force. So next, let's take a look at another example problem. In this example problem, we have 2 clay balls, one with a mass of 0.5 kilograms, one with a mass of 0.3 kilograms. They travel towards each other, they stick together when they hit, so this must be a perfectly inelastic collision. The 0.5 kilogram ball travels with an initial velocity of 2 meters per second. The 0.3 kilogram ball travels at 4 meters per second before the collision, and we want to know what's the final velocity of the 2-ball combination after they stick together. So, as with many collision problems, it's helpful to draw a picture of what is happening before and after the collision. So before we have the collision, we have these 2 balls that are traveling towards each other, and I'll just label them ball 1 and ball 2, and they're traveling towards each other, and they have different masses. I'll label this one as the M1 and this one as M2. And M1, we'll let that be the ball that's traveling with a speed of 2 meters per second, and then the other ball is traveling at 4 meters per second in the opposite direction. So that's the before. Then after the collision happens, the two balls are stuck together and they have a combined mass of M1 plus M2, and they're traveling in some final direction. Now, I'm not completely sure which direction, which ball is going to win out, what direction the final lump will be traveling, so I'm going to guess and say that it's going this way. We'll see if my guess is right as we solve the problem. So, since this is a perfectly inelastic collision, since the two balls stick together, we can conserve momentum and write down that M1 V1 initial plus M2 V2 initial is equal to, so this is the initial momenta of the two balls, and that's going to be equal to the momentum of the final two-ball combination. This combination has a mass of M1 plus M2 and is traveling with some final velocity. And it's that final velocity I want to find. So to find that, I just need to divide both sides of this equation by M1 plus M2. And that will give me that the final velocity is equal to M1 V1 initial plus M2 V2 initial divided by the sum of the two masses M1 plus M2. So then we can go ahead and plug in some numbers. So M1, the mass of the ball that's traveling at 2 meters per second, is 0.5 kilograms, traveling at 2 meters per second. And that ball is traveling to the right, so that's a positive 2 meters per second if I assume that the positive x direction is to the right. Then the 0.3 kilogram ball is traveling with a velocity of 4 meters per second, but it's traveling in the negative x direction, so I better put a minus sign in when I plug in the velocity of that ball. Then the sum of the two masses would be 0.5 kilograms plus 0.3 kilograms. And if I put that into a calculator, I get a final velocity of negative 0.25 meters per second. And so it looks like this picture that I drew is correct. I have a negative velocity, so it's traveling in the negative x direction. So the speed of the ball is 0.25 meters per second, and it is in a direction that is towards the 0.5 kilogram ball. So this statement would be true even if I reversed my picture and had the 4 meter per second ball traveling to the right and the 2 meter per second ball traveling to the left initially. So I could have swapped this around and I would get the opposite sign, but the statement that it's towards the 0.5 kilogram ball would still be true. All right, so next let's think about this question. A skater is standing still on a frictionless ice rink. Her friend throws a frisbee straight at her. In which of the following cases is the largest amount of momentum transferred to the skater?